and today I'm going to be presenting on the angular dependence of cosmic rays using the Cosmic Watch desktop muon detector. So let's start off with some definitions first. Cosmic rays are high energy radiation that comes from space from various sources like the sun or other galaxies. They're mostly made up of stuff like protons or helium nuclei, but they can contain heavier elements as well. And when they travel to the Earth from outer space, a lot of their energy is scattered away due to interactions with the Earth's atmosphere or Earth's magnetic field or solar wind or background radiation. There are many different ways. So that means that by the time the cosmic rays reach the surface of the Earth, they have much lower energy than when they started when they entered the Earth's atmosphere. And as the cosmic rays collide with the particles in the atmosphere, they split into mesons, which are particles that are made of two quarks. And most commonly, they split into pi mesons or k mesons, which happens around 15 to 20 kilometers above the surface of the Earth. And these mesons can come either neutral or charged. And the neutral mesons will interact with gamma rays and be scattered away for the most part. But the charged mesons will have further interactions with more particles in the atmosphere, which causes more splitting into more particles. And this causes a process called a particle shower. And about 99% of the time, a charged pion will decay into a muon and a muon neutrino. And about 63% of the time, a charged kaon will decay into the same products. And while neutrinos are notoriously hard to detect, we are easily able to detect the muons at the Earth's surface that were produced by these showers. Cosmic rays roughly follow Poisson statistics, so the probability to observe K cosmic ray events occurring at a rate R within some interval T is given by this distribution. So I will be focusing on the angular dependence of these cosmic ray muons. So why does the distribution depend on angle in the first place? Well, let's take two examples of rays. One is ray A, which is at a large angle to the vertical, and one is ray B, which is vertical. And if we use trigonometry, we know that the path traveled by A is going to be larger than the path traveled by B. And we've learned that cosmic rays are very sensitive to interactions with particles in our atmosphere. So that means that ray A is going to collide with more particles and lose more of its energy as it reaches the Earth's surface. And as a result, we see fewer rays like ray A at Earth's surface at all. So we will detect fewer cosmic ray muons at larger angles to the vertical. And one of the simplest angular distributions that follows these rules is going to be the cosine squared distribution, which you can derive if you assume some uniform distribution for the particles in the air and their interactions with the cosmic ray muons. And the goal of this experiment is to test the validity of this approximation and see what potential sources of uncertainty can lead to deviations. So I will be using the Cosmic Watch desktop muon detector, which was developed by Spencer Ixani. And the apparatus is a plastic scintillator with a silicon photomultiplier, or a SIPM, and it's put inside of an aluminum case. And muons travel through the aluminum case and hit the plastic of the scintillator. And this excites the particles of the scintillator. And when the particles de-excite, they release photons along the path of where they were excited, which just so happens to be the path that the muon traveled to get there. And this process produces a current discharge in the SIPM. And a microcontroller, a TNC 4.0, can convert that current to a corresponding voltage. And that itself is going to be proportional to the number of photons which triggered the event, or which were discharged in the SIPM, which in turn is proportional to the number of muons that created the discharge. Various bits of information are stored in a micro SD, such as the temperature, the timestamp, voltage, or pressure, and other things. Very importantly, it stores the dead time and whether the event was coincident or not. The dead time refers to the amount of time where the microcontroller is performing some computation, for example, converting the SIPM current into the voltage. And during that time, it can't store any new information that comes in during that time. And for this detector, the dead time is on the order of a few microseconds, so it's quite small, but it still makes quite a difference if you're calculating the rate. So we have to make sure to subtract it out of the total time when we're calculating the rate, which is the total number of muons you detect over the total time. And if you connect two cosmic watches together using the Ethernet cable, this is called coincidence mode. And you can store coincident events, which are events where both detectors detect the same event. And we represent it using a binary bit. So what exactly is this coincidence, and how do we know that these are actually coincident events? We define two events on two different detectors to be coincident if they occur within 3 microseconds of each other. And since the coincident detectors are hooked up with an Ethernet cable, we can determine which events are coincident by comparing the timestamps of both events on each detector. But what happens if there are two events which just so happen to occur within 3 microseconds of each other, but they're not actually the same muon? So let's assume that this happens. We can use Poisson statistics to see how often this happens. So here I let R1 be the count rate on one detector and R2 is the count rate on the other, which is around 3 hertz at sea level. And I let tau be this 3 microsecond coincident window. And the rate for accidental coincidences within the time span of tau is given by this product here. And the factor of 2 comes from the fact that either of the two detectors could have detected the event first. And if you plug this into the probability distribution, you see that 1 out of every 55,000 events should be an accidental coincidence. And this results in about 5 coincident events per day. So we associate an uncertainty with this of sigma rate accidental of this 1 over 55,000 in the coincident rate. And we'll take this into account when we talk about our uncertainties a little bit later. We know that these events will largely be due to muons, since the other particles that make it to the surface of the Earth, like alpha and beta particles, or equivalently just random protons and electrons, will scatter away before they reach the detectors, or the aluminum case will attenuate them so that they never reach this until later in the first place. So most of the events that we see, a large majority of the events that we see will be due to muons. So I built a little rig made out of a textbook and a cutting board, very professional. And I attached the two detectors in coincidence, separated by 4 centimeters from the exteriors of their aluminum cases. And to measure the angle, I marked a point on the cutting board, which I've represented here with this yellow X. And then I had to measure the height and length of each of these setups. So to measure the height, I put a measuring tape on my table and then measured up to the point that I had marked on the cutting board, to this yellow point. And I let that be the height. And then to measure the length, I put a bamboo rod on the table and put the end of the measuring tape where the bottom of the bamboo rod is. And then I moved the bamboo rod to the cutting board so that the edge of the bamboo rod would hit the tape where the cutting board, where the length of the cutting board was. And I let that be the length L. The angle from the vertical, which I've shown here, is given by the arctangent of the length over the height. And to decrease the statistical uncertainty, I repeated the measurements, each of these measurements 4 times, and then I used the average of them when I calculated the angle. For each of these angles, I gathered the data for about 10 hours at roughly the same times every day. And I used 13 different angles from the vertical, from 0 to pi over 2, where pi over 2 is horizontal. And the detectors are sensitive to altitude. So it's important to note that I took this at 12 meters above sea level in Cambridge, where the coincident rate is roughly about 0.14 hertz if the detectors are stacked on top of one another. So to perform a quick sanity check, let's see if the rates are roughly flat as we collect data. To do this, I took the binned rate data in bins of 240 seconds, and then I plotted it over the total runtime. And as you see here, there are fluctuations, but they roughly stay at about the same rate on average. So we can see that the distribution does not fluctuate unreasonably from the average rate, which is a nice sanity check. And so this means that we're allowed to use the average value of the rates throughout the entire day to test the angular distribution for each angle. And to do that, you use the average rate, which is the total counts over the entire day over the live time. And remember, the live time is the total time minus the dead time, because the microcontroller is not active during that time. So here's what it looks like. I used those 13 angles ranging from 0 to pi over 2. And for the rate determined at the horizontal, we actually have to divide the total rate by 2, since the detectors can receive muons from either direction, not just one. The distribution matches qualitatively pretty well. I've included error bars in the rates and the angles, which I will discuss later regarding the uncertainties. So the uncertainties in this experiment come largely from the measurement of the angles. It's really hard to measure the angles when you have a very amateur setup, as I did, because I don't have equipment. So I guess that I measured within 1 centimeter of the actual height or length of my setup. And since I measured 4 times, the uncertainty is 1 over square root of 4, how many times I did the measurement, which is half of the actual uncertainty that I thought I had. So overall, I have an uncertainty in the average of the height and length of about 1/2 centimeters. We can propagate this uncertainty into the angle by using the general propagation formula, and I've listed this here for this particular function. And this gives us an uncertainty of about 0.1 radians. This is included in the horizontal error bars on my plot here. And we also have to take into account that the cosmic rays interacting with the particles in the ceiling of my apartment or the windows of my apartment could create additional sprays that would not normally be detected if I had performed this experiment outside. We could take care of this by shielding one of the detectors indoors so that those coincident events that occur from sprays in my window or my ceiling are reduced, but I did not do that. There is also uncertainty in the counting of the muon events. Generally, the uncertainty when you're doing a counting experiment is given by the square root of the number of counts you have. And so when we compute the rate, we have to propagate this through. And this leads to an average uncertainty of about 4 times 10 to the minus 4 hertz. We also have this accidental coincidence uncertainty that we talked about earlier, the 1 in 55,000. And so I also took this into account in the vertical error bars in this plot. Okay, so why should you care about this experiment at all? Well, first, this area of physics is the kind of stuff that physicists are researching today. For example, the Ice Cube Neutrino Observatory uses principles that are very similar to this. So it's important that students have a scaled down example of this that we can understand. This is also a good example of particle detection methods. Here we use scintillators, so it's important to understand how those work and what parts go into particle detection. Lastly, it's a system that follows Poisson statistics, which is always good because it makes calculations easy. And the muon angular dependence follows the simplest possible angular distribution, the cosine squared law, which also makes it easy to check as a particle physics experiment. Thank you to the usual crowd, especially to John and Spencer. And are there any questions?